Hey everyone, welcome back to another lesson in MCR3U. Today we'll be continuing our exploration in applications of trigonometric functions, specifically looking at, again, sine and cosine. So here, if we look at the first example, it says in one area of the Bay of Fundy, the tides caused the water levels to rise 6 meters above sea level and to drop 6 meters below sea level. One cycle is completed approximately every 12 hours. So here again, it says 1 hour is completed approximately every 12 hours. What that tells us here is, again, because it's one cycle, we see that that represents, again, our period. So then it continues with, assume that changes in the depth of water over time can be modeled by a sine function. So that would be our parent function that we'll use to indicate any transformations. Here it says if the water is at average sea level at midnight, so average sea level at midnight, and what that will tell us here is that it is on the axis, t is equal to 0. And the tide is coming in, which means that it is getting deeper. So when the tide is coming in, then that means it is getting deeper. Draw a graph to show how the depth of water changes over the next 24 hours. So again, 24 hours, one cycle is 12 hours, which means that the next 24 hours means that here we are representing two cycles. And assume that at low tide, the water level is 2 meters. Okay, so here we're given a graph, and there's a couple of things that were provided. Again, the water level again rises 6 meters above sea level, and again 6 meters below sea level. And so what that tells us is that our amplitude will have to be equal to 6 meters. Okay, so here we see that again at low tide, the water level is at 2 meters. Again, but our amplitude is at 6, which means that here we know that our axis will be at y is equal to 8. Again, because again, the difference between 2 and 8 will be 6, which is our amplitude. Here we see that our period, again, that we looked at is equal to 12. This means here that our k value again is equal to 360 over 12. And that will give us 30. So here k is equal to 30. Okay, so now let's label the graph. And so here again, the x-axis, we'll label this time since midnight. In hours. And then on the y-axis, we'll label this the water depth in meters. And so here on the axis, on the x-axis, we'll go up by 1. And we'll just label this again. Here going up by 1, and then we'll show every 3. And here we'll go up to 24 on the x-axis. And then on the y-axis, we'll go up by 1 as well, but we'll show again here every 2. So here's 2, 4, 6, 8, 10, 12, and 14. So again, here we know that our axis is as y is equal to 8. So we'll represent that again with a dotted line. So here, y is equal to 8. And again, we know that our amplitude is at 6 meters. Again, here it starts again here at 0 and 8. So here again, it starts at the axis. It reaches again the maximum at 14. And 3 here goes back to 0 at 6 hours. It reaches the minimum, or the low tide water at 9 hours. And then again, it continues this cycle. So at 12, again, it goes back to the axis at y is equal to 8. And at 15, it reaches the maximum. And then 18, it's back to the axis. At 21, back to the minimum. And then finally at 24, it goes back to the axis here. And so that represents, again, our 2 cycles. And so here, if we look at the equation of the graph, we see that, again, so it starts on axis, and it is going up, which means that here this will be positive. Okay, and then as we create this equation, we'll just let a couple of variables represent things. So here we'll let d represent, again, the water depth in meters. And we'll let t here represent time in seconds. So here, if we write our equation, we get d is equal to our amplitude, which is 6, sine k value is 30, so 30 t. And then here we see that our axis is 8, so then plus 8. So the equation here is d is equal to 6 sine 30t plus 8. Okay, so here, part C, it says, at what times during the 24 hours is the buoy at 4.5 meters above sea level? And so here we see that, again, sea level is at 8 meters, which means here that therefore, again, we take our 4.5 plus 8, which is equal to 12.5 meters. So that would be when, again, we're going to use that distance to calculate when times, again, this buoy is 4.5 meter above sea level. Here we can sub it into our equation. So we have 12.5 is equal to 6 sine 30t plus 8. We'll subtract 8 from both sides, so we'll be left with 4.5 is equal to 6 sine 30t divide both sides by 6. And we'll first again let here 30t is equal to a, and then we'll divide by 6 here. So here we have 4.5 over 6 is equal to sine a. Here we see that when we calculate it, we get a is approximately equal to 49. So here, again, if we draw our grid, and here we see that this has to be again when sine is positive, so it'd be in quadrant 1 and quadrant 2. So here, if this is our beta, again, we see that this would be 6, this would be 4.5. And in quadrant 2, again, we would have, again, 6 and 4.5. Again, 4.5 being the opposite, and then 6 being the hypotenuse. And so again, if we looked at sine of beta is equal to 4.5 over 6, again, we see that then beta would be equal to sine -1 of 4.5 over 6, which gives us that value that we saw, again, of 49 degrees. So now that we know that, again, where our beta is 49 degrees, again, there is, again, that's would be in quadrant number 1, but we also have to see it in quadrant number 2. So here, again, we also take a is equal to 180 minus 49, and so here a can also equal to 131. What we have to do here is, since we let 30t is equal to a, we have to sub that back in. So we have one equation, so 30t is equal to 49, and t is equal to 1.6 hours. And then we also have the other equation, which is 30t is equal to 131, and here t is equal to 4.5 hours. Here we see that we have t is equal to 1.6 hours, and then t is equal to 4.4 hours. Here again, if it starts, again, in the 24-hour period, again, one cycle is completed approximately every 12 hours. So here, if we take, again, our 0.6 multiplied by that by 60, again, that's equal to 36 minutes. And so if when t is equal to 1.6 hours, we see here that, again, it would be 1:36 a.m. But we also have to consider the after the one cycle, so plus 12. So again, it's 1:36 again, or 1:36 p.m. So 1:36 a.m. or 1:36 p.m. And then for the 4.4 hours, if we take again our 0.4, multiply that by 60, that will give us 24 minutes. So here when t is equal to 4.4, again, it would be at 4:24 a.m. Or again, in that next cycle, we add by 12 at 4:24 p.m. So what that means again is we can write our therefore statement. So here, therefore, the water is 4.5 meters above sea level. 1:36 p.m. Sorry, 1:36 a.m. or p.m. and 4:24 a.m. or p.m. Okay, so let's look at example number 2. So example number 2 says a certain mass is supported by a spring so that it is at rest at 0.5 meters above the tabletop. And so here it's at rest 0.5 meters above the tabletop. That represents our axis. The mass is pulled down 0.4 meters. So down 0.3 meters and released at time 0. Okay, so that here again, that will be our amplitude. Again, here. And here again, t is equal to 0 is going to be our minimum. Okay, and here, so it creates a periodic up and down motion called the simple harmonic motion. It takes 1.2 seconds for the mass to return to its lowest position each time. Okay, so here our 1.2 seconds will represent our period. Here it says again, draw the graph showing the height of the mass above the tabletop as a function of time for the first 2.4 seconds. Okay, so here again, our amplitude is equal to 0.4. Our axis, here we see that it's at y is equal to 0.5. Our period is again that 1.2 seconds. So again, for our k value, we take 360 divided by 1.2. And here we get that equal to 300. And here it starts, again, we're looking at it as a cosine graph. So here, if we look at a cosine graph, again, it starts on a minimum, and therefore cos would be negative. Okay, so here, if we graph this, and we'll go from our time, and our time in seconds, then we'll go up here by 0.1, and we'll represent. And here we'll represent every 0.4. And so we'll finish here off at 2.6. Here in our y-axis, that will represent our height of the mass in meters. So here we'll go up by 0.1 again, and we'll start at, again, we'll show every 0.2, so 0.2, 0.4, 0.6, 0.8, and we'll finish off here at 1. So here again, we know that our axis is at 0.5. So our axis here is at 0.5. And here again, if and our axis is at y is equal to 0.5, again, and it starts at a minimum, and our amplitude is 0.4. So here we'll start at 0.1, and then at here 0.3, it'll reach the axis. Then at 0.6, it will reach our maximum here, which would be 0.9, and then it'll go at 0.9 seconds, it'll go back to our axis. Then 1.2, it'll go back to the minimum. 1.5, we'll be back at the axis. So we can connect these points. Then at 1.8, it'll reach back to the maximum in terms of height. And then 2.1, go back to the axis. And then finally here at 2.4, we'll be back at the minimum. Okay, so here it says write an equation for the function. And so first thing here is, again, we'll let a couple of these variables. So we'll let h represent the height in meters. And here we'll let t represent time in seconds. So here again, we said, again, it starts on a minimum, which means therefore our cos function is negative. So here we have h of t is equal to negative. Again, our amplitude is 0.4, so 0.4 cos k value is 300. So 300 t plus 0.5. And so here it again wants us to determine a few things. Again, it wants us to determine the height of the mass above the tabletop after 0.3 seconds, then 0.7 seconds, and 1.2 seconds. So here we'll sub those in. So here we have h of 0.3 is equal to negative 0.4 cos 300 times 0.3 plus 0.5. And so here h at, again, 0.3 seconds will be 0.50. H of 0.7 seconds. Again, if we sub that back into the equation, negative 0.4 cos 300 times 0.7 plus 0.5. Here again, we see that we sub that in. H at 0.7 seconds is going to approximately 0.85. And then finally here at 1.2 seconds, again, we'll sub it in. And so here we see that h at 1.2 seconds will be equal to 0.10. And again, you can verify using the graph itself to see the answers. Again, but here, right there for statement. So therefore, the height at 0.3 seconds is 0.50 meters. At 0.7 seconds is 0.85 meters. And at 1.2 seconds is 0.10 meters.